On this video we're going to cover up a new topic, which is shear stress in twisting. On this video we're going to be focusing especially on round shafts and tubes which we are twisting, and later on in this course we'll be discussing also other types of cross-section profiles. But what is shear stress in twisting? So you can imagine if you have a round axle and we're applying a pure torque at the end, the axle wants to twist. It wants to be twisted like so. In this image on this slide you can see there's an example of a short section of a round shaft which we have a torque at the end, here torque T, which is twisting this axle. And now when we're applying this torque you can see that the axle is twisting. These lines on the axle are showing how the material is twisted. Now in strength of materials we have a way how we can calculate how much the material has twisted, how many degrees it has twisted, and also we can calculate what is this maximum shear stress on this piece of material that we are twisting. Previously we have learned that we have strain in materials. We have normal strain and shear strain. The shear strain in case of pure twisting is defined so that if we take a small portion of the material on the surface of the material of the piece of which we are twisting, and we take a look at the material, we can see that it has changed shape. It has become diamond-like shape, and the shear strain is the angle here. So if we did not have any stress here, this piece of material, it would be rectangle shaped, but when we have applied a load there, it has changed to diamond shape, and the angle there is now the shear strain. Okay, so how do we calculate the strain, the shear stress, and the change of the angle on pure twisting torque? Well, in order to be able to calculate the change of the angle, which is here, we need to know the torque, T, we need to know the length of the material, L, we need to know G, which is shear modulus, which is a material parameter just like Young's modulus, and we also need to know a new thing which we call polar moment of inertia. This one is also called second moment of inertia. On this video we're going to learn how we can calculate the polar moment of inertia for round axles and round tubes. Okay, so before we go on how we calculate the Ix, which is the second moment of inertia or polar moment of inertia, let's talk about the shear stress. So when we have a round axle like this one and we're applying torque to it, the shear stress profile, follows this kind of shape. So the maximum value for shear stress is always at the outermost surface of the material, and when we go to the very middle of the material there is no shear stress at all. Similar thing applies to pipes. So in this case we have the same size of material, the outermost diameter is the same, but instead we have now a hole in the middle, so it is a pipe. The stress distribution is exactly the same, exactly similar to the stress distribution of solid shafts, but we just don't have stress in here. Obvious reason is that we have no material there. When we want to calculate the shear stress, what we do is that we use this equation. Tau, because it's shear stress, we're again using tau. Tau equals to torque divided by the cross-section parameter Ix, which describes the stiffness of the cross-section, multiplied by the radius. In most cases, we are always interested on the maximum value of the shear stress, which is always at the outermost surface of the material, and therefore in many cases we, instead of using this equation, we can also use this equation, which always gives us the value for the shear stress at the outermost surface of the material. In this case, the torque would be divided by torsional section modulus Wx, and the Wx in case of round axles or tubes is just simply the Ix divided by the R maximum, so maximum radius of this piece. Important thing about calculating this, just like everything else in fundamentals of strength of materials, is that we always like to use newtons, millimeters, so we end up with megapascals. So how do we then define this new material property which we are talking about, the Ix? Well, the Ix is for solid circle cross section is very simply defined. Ix is pi times d diameter power to 4 divided by 32. Very simple. Wx, you can get the Wx by dividing the Ix with the R maximum, or you can use this equation straight away, which is pi times diameter power to 3 divided by 16. Well, what about then the stress distribution at pipes cross section when we have pipe? Well, the Ix, the parameter which describes the stiffness, that is calculated using this equation here, in which the alpha, which we see in here, is a new term, and the alpha is the inner diameter divided by the outer diameter, and Wx is Ix divided by R maximum. And for that you can also use straight away this equation. So that's the theory for calculating the shear stress and calculating the angle of twist for round cross-sectioned materials. In the example videos you can see how these are used in practice.